Imagine for a second that you just bought the most incredible state-of-the-art smart home.
Okay, it's nice.
Right. It's got voice-controlled everything, windows that tin automatically, a fridge that tracks your groceries. But there is a massive catch.
There always is.
Yeah, the plumbing and the electrical wiring behind the walls are completely invisible. Half the pipes are just randomly disconnected. And get this, the local utility only guarantees water pressure on Tuesdays.
Oh, wow. Yeah, that sounds like a total nightmare.
Exactly. It's a beautiful house, but living in it would be a constant, logistical stress test.
It becomes an exercise in anxiety rather than actually enjoying the technology. You'd spend all your time thinking about the infrastructure, not the house itself.
And that feeling, managing this invisible, somewhat unreliable infrastructure, that is exactly what we are dealing with when we look at the electric vehicle landscape right now.
Oh, absolutely.
We spend so much time focused on the shiny new cars, right? The 0 to 60 times, the massive touchscreens. But if you are thinking about buying an EV, or maybe you manage a fleet of delivery trucks, or honestly, if you just want to understand the future of the power grid, this deep dive is going to reveal something crucial.
Yeah, the real revolution isn't the cars themselves.
Right. It's the invisible infrastructure, the grid logistics, and the software keeping those cars alive.
The vehicle is truly just the tip of the iceberg at this point. I mean, the massive hidden transformations happening in the EV ecosystem are entirely about data management and energy distribution.
And we have a really fascinating stack of sources to pull from today to prove that. We're looking at government reliability reports from NREL, the National Renewable Energy Laboratory. We've got market analyses on predictive maintenance and portable chargers.
Which are wild, by the way.
Totally. And we're also pulling from PR announcements on mobile charging networks, plus some incredibly intense technical reports on megawatt-level commercial charging. So, okay, let's unpack this.
We really should start with the reality on the ground, which is just a story of massive physical bottlenecks. Because, the vehicles are absolutely here.
Oh, yeah, they're everywhere.
Right. Global EV sales hit a record 14 million units in 2023. That's a 35% jump from the previous year. We are manufacturing the cars at a staggering rate.
But the public infrastructure is severely lagging behind that. Like, the statistic that jumped out at me from these reports is honestly jarring. In the U.S., the ratio of electric vehicles to public charging ports is 29-1.
Yeah, it's a huge problem.
29 cars out on the road fighting for a single public plug? That's just nuts.
It really is. And that ratio creates what the industry calls charging deserts. It triggers severe range anxiety. And surveys consistently show that is the single greatest barrier to EV adoption. People are just terrified of getting stranded.
Understandably so.
But relying on the NREL report we have here, simply putting more physical chargers in the ground doesn't actually solve the problem. The hardware has to, actually function when you pull up to it.
Which brings up a huge pain point, the failure rate. It's less like a broken wall outlet and more like trying to use a credit card in a foreign country where the reader just refuses to talk to your bank.
That's a perfect analogy.
The electricity is sitting right there in the grid, but the digital handshake fails, or the screen is dead and you just can't get the charge.
That is highly accurate. NREL notes that the reliability of public chargers has become a systemic issue. It's not just vandalism or cut cables, right? It's software communication errors.
Right.
Or payment processing timeouts, and even internal cooling system failures. It became such a recognized crisis that the federal government actually had to step in.
Wait, really? The government got involved?
Oh, yeah. They mandated a strict 97% uptime requirement for any federally funded EV project.
Wow. But mandating 97% uptime is one thing. How do they actually enforce that when the hardware is scattered across millions of square miles?
Well, they backed the mandate with funding. The government launched a $100 million accelerator program specifically to fix or replace broken legacy chargers.
Okay, that makes sense.
And alongside that, they formed the ChargeX Consortium. This brings the national labs, charger manufacturers, and automakers into one room to standardize those digital handshakes you mentioned.
Oh, nice.
Yeah, they're actively trying to solve vehicle-to-charger communication errors so that the car and the charger speak the exact same digital language every single time.
That structural work is obviously crucial for the long term, but building fixed, reliable stations requires massive capital. You have to get local permits, trench through concrete, upgrade local transformers.
It takes years.
Exactly. If I'm an EV owner right now or a delivery company running out of juice on a route, I can't wait 2 years for a permitted station to be built.
And the market recognized that exact gap. It's driving a major shift toward charging as a service. So instead of making the car go to the charger, companies are bringing the charger to the car.
Which is such a wild concept.
Our TechSite report highlights the explosive growth here. A prime example is this company called BCharge DV. They just announced a massive expansion rolling out into 100 U.S. cities, alongside their first international launch down in Mexico City.
So they are essentially operating a fleet of specialized rescue vans.
Yeah, exactly. These are commercial vans equipped with heady, high-capacity battery packs and onboard fast-charging tech. You just open an app, drop a pin on your location, and a technician drives the van straight to your parked car.
That is so convenient.
Right. In about 15 to 30 minutes, they transfer 50 to 100 miles of range into your vehicle. But the real innovation isn't just the hardware, it's the business model. They're pushing an unlimited mobile charging subscription for a flat monthly fee.
Ah, I see the psychology there. You aren't just paying for the electricity, you're paying a premium to completely eliminate the anxiety of being stranded. It's like a safety net subscription.
Exactly. The peace of mind is the actual product. And the technology delivering that power is evolving really fast. The sources also detail companies like Ion Dynamics, who have developed a unit called the Flashbot.
The Flashbot is fascinating. It's literally an autonomous charging robot that roams around parking lots.
Yes, it navigates commercial parking structures entirely autonomously to charge cars on demand.
So you don't even have to hunt for a spot.
Right, you don't need to circle the lot looking for a dedicated EV spot with a permanent plug. You park in any standard space, summon the Flashbot via your phone, and it comes to you.
That feels like science fiction.
It does. It acts as a level 3 DC fast charger, which means it bypasses your car's internal converter to push direct current straight into your battery. Then it unplugs and just rolls on to the next customer.
I imagine commercial property owners would love that. They don't have to spend $500,000 ripping up their asphalt to install permanent infrastructure. Just buy a few robots.
It's a huge cost saver.
But summoning a battery on wheels or an autonomous robot feels like a great fix for a passenger sedan. A little van dropping off 50 miles of range works for a Honda or a Tesla.
Sure.
But what happens when the vehicle is a massive Class 8 semi-truck carrying tens of thousands of pounds of freight? A mobile van isn't going to make a dent in that battery.
Not at all. The energy requirements for heavy freight are on an entirely different scale. And that brings us to the ZR report on the Megawatt Charging System, or MCS.
Okay.
This is a newly developed standard designed specifically for heavy commercial vehicles. Think long-haul trucks, city transit buses, heavy mining equipment, and even electric ferries operating in shipping ports.
To put this into perspective for you guys listening, a standard fast charger you might see at a grocery store, like a really high-end one, maxes out around 350 kilowatts.
Right.
And the MCS standard is designed to pump 3.75 megawatts into a single truck. That is 3,750 kilowatts. That's not just a fast charger, that is the equivalent power draw of a small neighborhood being forced through a single cable.
It's wild. The physical engineering required to safely deliver that much energy is staggering. We are talking about pushing up to 3,000 amps and 1,250 volts of direct current.
But wait, if you push that through a standard heavy-duty copper cable, wouldn't the resistance generate so much heat that the cable would just melt?
It would literally melt and catch fire within seconds.
So how do they stop it from melting? You can't just make the copper thicker, or the cable would be too heavy for a human to even lift.
Exactly. So they use active liquid cooling. The charging cables and the connectors themselves have internal conduits running alongside the electrical wires.
Liquid inside the electrical cable.
Yes. A cooling system continuously pumps a synthetic liquid coolant through those conduits while the truck is plugged in. It extracts the immense heat generated by the electrical resistance and carries it back to a radiator in the main charging unit.
Wow.
This keeps the cable safe to touch and flexible enough for a driver to physically handle.
Pumping coolant through an electrical cable carrying thousands of volts, I mean, the margin for error there seems incredibly small.
Very small.
But it's not just the physical heat, right? There has to be a data component. If you are delivering a neighborhood's worth of electricity, the charger and the truck must be communicating constantly to avoid overcharging a cell or causing an arc.
Yes, the data management is just as complex as the thermal management. With the combined charging system, or CCS, which is the current standard plug for most passenger EVs, the car and the charger communicate using power line communication, or PLC. PLC essentially shouts basic digital data over the same physical wire that is delivering the electrical power. It works, but it's a noisy, relatively slow communication method.
I'd imagine shouting data over a line carrying 3.75 megawatts creates a massive amount of static and interference.
It creates an unacceptable level of interference.
Right.
When you are dealing with megawatt charging, the timing of the power delivery has to be millisecond perfect.
Yeah,
You cannot afford a lost packet of data when you are managing 3,000 amps.
that makes sense.
So the MCS standard actually abandons PLC entirely. They're upgrading the communication cables inside the plug to 10 base T1S automotive Ethernet.
Wait, they are essentially installing a dedicated high-speed wired internet connection between the truck and the charger?
That's exactly what it is.
Mhm.
That dedicated Ethernet lane handles a massive encrypted data flow. It ensures the complex charging protocols, the thermal sensor readings, and the safety checks happen flawlessly in real time, completely isolated from the electrical noise.
That is incredible engineering.
And this technology is moving out of the lab and into the real world right now. The Milans network, which is a major joint venture by Daimler, Traton, and Volvo, is already rolling out these MCS hubs across Europe.
Oh, so it's really happening.
Yes, Germany recently approved a 1.6 billion euro funding program dedicated to heavy truck infrastructure, and they are explicitly requiring 130 of those new hubs to feature at least 1,000 kilowatt MCS charging.
Okay, so the engineering exists to push this massive amount of power. But taking a step back and looking at the macro level, if we're delivering megawatts to commercial trucks while simultaneously plugging in millions of passenger EVs when everyone gets home from work at 6 p.m.,
Oh, the grid.
right, the sheer amount of electricity required is staggering. I don't understand how the local power grids, which are often decades old, survive that kind of concentrated surge in demand.
They often don't. The grid strain is a highly critical bottleneck. The Arvel report we reviewed focuses heavily on this. In the Netherlands, the power grid is already facing such severe congestion from EV adoption that grid operators took drastic measures.
What did they do?
They actually advised shutting down public EV charging stations entirely between the peak hours of 4 p.m. and 9 p.m.
Wait, if the grid in the Netherlands is so congested, why did operators advise shutting stations down instead of just, I don't know, building more substations or upgrading transformers?
Because upgrading physical grid infrastructure is incredibly slow and monumentally expensive. Replacing local transformers, running thicker high-voltage lines, and building new substations can take years of permitting and cost billions of dollars.
Oh, right.
When everyone in a city turns on their air conditioning, their ovens, and plugs in their EVs at the exact same moment, the existing transformers physically overheat and trip to prevent a catastrophic blowout.
That's like everyone in a city turning on their AC, microwave, and hairdryer at the exact same second. The system just trips.
Exactly.
So the infrastructure can't handle the peak, and we can't build new transformers fast enough. How do we solve it without just banning charging in the evenings?
We solve a hardware problem with software. The first layer of defense is called controlled charging, or V1G. This is unidirectional smart charging.
Okay.
Instead of a dumb plug that immediately pulls power the second it's connected, the EV, the charging station, and the local utility grid communicate via software APIs.
So you plug your car in at 6 p.m., but the power doesn't actually flow yet.
The car and the grid negotiate. You might tell your app you need a full battery by 7 a.m. The grid tells the charger that demand is currently peaking. So the charger simply waits until 2 a.m., when citywide demand is at its absolute lowest, to actually draw the power.
That's brilliant.
The Arvel report notes that by implementing controlled charging alone, a utility company can operate up to 6 times as many charging stations on a single existing transformer without ever exceeding its physical peak capacity.
6 times the capacity just by shifting the schedule. The physical wires are identical, but the software prevents the bottleneck.
But V1G is just the baseline. The real paradigm shift in energy management is V2G, or vehicle to grid, and V2X, vehicle to everything. This concept completely flips the script.
How so?
Instead of viewing millions of EVs as a massive drain on the electrical grid, V2G turns those vehicles into mobile, decentralized energy assets.
This implies the car isn't just taking energy, it's physically pushing electricity back out of the battery and into the city grid.
That is the core mechanism of bidirectional charging. The cars act as a distributed battery storage network. An EV battery stores direct current, or DC power. The city grid runs on alternating current, or AC.
Right.
VDG requires specialized bidirectional inverters that can take that stored DC power, convert it perfectly into AC power, synchronize the phase frequency with the local grid, and push it back out.
So during a peak demand event, like a blistering hot summer afternoon when everyone's AC is blasting, the grid could theoretically pull a little bit of power from thousands of parked EVs to prevent a rolling blackout.
Yes.
And then it replenishes those cars in the middle of the night when energy is cheap, maybe when wind turbines are generating excess power.
Exactly. And this is far beyond the whiteboard phase. It is happening right now. The text highlights several active implementations. There is a major joint venture called DAEV, backed by the French utility giant EDF, that is developing and deploying this bidirectional technology.
Oh, wow.
In Denmark, the Parker project successfully proved that fleets of EVs can reliably provide frequency regulation and grid stabilization services.
That's huge.
And Pacific Gas and Electric, PG&E, is running a pilot program in California where customers use their vehicles to power their own homes during temporary grid outages. More importantly, those customers earn financial incentives by allowing the utility to adapt their charging and discharging based on grid demand.
So we have autonomous robots roaming parking lots, we have liquid-cooled megawatt cables for semi-trucks, and we have millions of cars actively converting and trading electricity back and forth with the power grid in real time to prevent blackouts.
It's a lot to manage.
Managing that level of complexity is staggering. I mean, a human mechanic plugging in a diagnostic tool or a simple check engine light on a dashboard, that is completely insufficient for a system this dynamic.
Oh, entirely. The hardware is only as capable as the software managing it. Which brings us to the Data report on the predictive car maintenance application market. The growth in this sector really reflects the shift towards software-defined vehicles.
Okay, what are the numbers looking like?
Right now, the predictive maintenance market is valued at $4.8 billion. Over the next decade, by 2034, it is projected to explode to $14.7 billion.
So this is far beyond like an app reminding you to rotate your tires. We are talking about software that monitors the internal physics of the vehicle.
Exactly. Electric vehicles introduce entirely new, highly expensive failure modes that traditional gas engines simply do not have. There are no spark plugs or timing belts to worry about.
Right.
The critical vulnerabilities are the complex thermal management systems we discussed earlier, and the battery's state of health, or STOH. A lithium-ion battery replacement for a mainstream passenger EV can cost anywhere from $8,000 to $22,000.
A $22,000 repair bill is catastrophic for a consumer, let alone a commercial fleet operator managing hundreds of vehicles. How does an app actually predict that a battery is going to fail before it happens?
It relies heavily on machine learning applied to vast data sets. A modern connected EV has hundreds of sensors constantly monitoring the powertrain. Predictive maintenance apps stream that data, looking for microscopic voltage sags in individual battery cells, slight increases in electrical resistance, or tiny thermal anomalies where one part of the pack is running just a degree hotter than the rest.
So the AI is detecting the earliest physical signs of degradation, like dendrites forming inside the lithium cells, long before a human driver would ever notice a drop in performance.
Precisely. The algorithms compare your car's real-time sensor data against the historical data of millions of other vehicles to identify the specific degradation patterns that precede a catastrophic failure. The report highlights that these predictive platforms can accurately anticipate component failures 7 to 30 days before the hardware actually breaks down.
Up to a full month of advance warning?
Yes.
That's incredible. You aren't reacting to a breakdown, you're preventing it entirely.
The financial impact of that advance warning is massive. The Data report details that commercial fleet operators utilizing these predictive platforms are driving down their total cost of ownership by 12 to 20%.
That's a huge margin for a fleet.
Even more critical for logistics companies, they are reducing unplanned roadside breakdowns by over 50%. You're fixing the degraded cell or the failing coolant pump in the depot on a scheduled Tuesday, rather than paying for an emergency tow truck when the vehicle dies on the side of the highway with a full load of cargo.
And because this is all software-driven, the car doesn't even need to go to a dealership to get smarter.
Nope. The report notes that over 71% of these predictive platforms are entirely cloud-based. This means the AI diagnostic models are constantly refined on centralized servers.
Oh, I see.
When the vendor improves the algorithm to detect a new type of thermal variance, they simply push a real-time, over-the-air update to your vehicle. The diagnostic capabilities improve continuously without a mechanic ever touching the car.
When you connect all of these pieces, it fundamentally changes the relationship we have with transportation. Looking through all these reports, they paint a picture of an electric vehicle revolution that has moved far beyond horsepower or battery size. The true innovations are entirely about logistics, predictive software, and macro-level energy management. We are moving from portable charging robots and megawatt liquid-cooled cables to grid-stabilizing bidirectional inverters and machine learning models forecasting their own mechanical
Kind of
failures.
a whole new world.
The car is no longer just a mode of transport, it is a rolling data center and a mobile energy asset.
It represents a complete architectural shift in how we view the grid and mobility. The physical vehicle is merely the hardware vessel. The real value is the software ecosystem and the energy network it plugs into.
Which leaves a fascinating final thought for you, our listener, to mull over today. We started out by talking about that imaginary smart mansion with the complex, invisible plumbing. But as we move into a future where our vehicles are constantly streaming gigabytes of data to cloud servers to predict their own degradation,
Mhm.
it's pretty where they're actively converting and trading electricity back and forth with the city grid, and where they can autonomously summon roaming charging robots when their voltage drops. Do we even really drive our own independent cars anymore? Or are we transitioning into an era where we are simply subscribing to a smart mobile node within a giant self-healing energy network? Think about that invisible ecosystem the next time you plug in.